SCR-based dimming systems employ thyristors, also known as silicon-controlled rectifiers, to regulate the flow of electricity. When a thyristor is in the off state, it obstructs current flow. Conversely, when it's in the on state, current is allowed to pass through. However, SCR exhibit a characteristic known as a low holding current, which implies that they necessitate a minimal amount of current to sustain their on state, even in the absence of a control signal. In scenarios where contactors are energized upon the activation of SCR within a non-dimming module facilitating current flow through the coil should ideally release when the SCR deactivate. Nevertheless, the inherent low holding current of SCR may lead to their partial activation, thereby impeding the complete release of the coil. An add-on resistor serves as a resistor interconnected in parallel with the contactor coil. Its function is to furnish a pathway for current flow, even upon the deactivation of the SCR, thereby guaranteeing the comprehensive release of the coil. The selection of an appropriate add-on resistor hinges on various determinants encompassing coil voltage, current, and release duration. As a general guideline, a resistor value approximating 10 to 20% of the coil resistance is typically recommended. To install an add-on resistor, firstly, disconnect power to the contactors. Secondly, locate the coil terminals on the contactors. Thirdly, connect one end of the resistor to one coil terminal. Fourthly, connect the other end of the resistor to the other coil terminal. Fifthly, restore power to the contactors. Upon installation of the add-on resistor, it is imperative to assess the functionality of the contactors. Manipulate the channels governing the non-dimming modules, alternating between upward and downward movements to ascertain the accurate energization and release of the coils. Additional considerations include firstly, employing a resistor with a wattage rating adequate to manage the current traversing the coil. Secondly, positioning the resistor in a well-ventilated vicinity to avert overheating. Thirdly, if the contactor coils persist in chattering subsequent to the incorporation of the resistor, experimentation with varying resistor values or consultation with a qualified electrician may be warranted. The role of the add-on resistor is pivotal in mitigating coil chatter, particularly within dimming systems predicated on SCR technology. By furnishing an alternate route for current dissipation, the add-on resistor forestalls the perpetuation of current flow through the contactor coil subsequent to the intended cutoff by the SCR, thereby facilitating dependable and stable contactor operation. The electrical resistance of a material or component is a measure of its opposition to the flow of electric current. It is measured in ohms, symbolized by the Greek letter omega. Resistance is a fundamental property in electrical circuits, influencing current flow and voltage distribution. Resistors are electronic components designed to provide a specific amount of resistance in a circuit. They are used for various purposes, including limiting current, dividing voltage, and providing a load. Resistors are available in a wide range of resistance values and power ratings. Ohm's law is a fundamental relationship in electrical circuits that relates voltage, current, and resistance. It states that the voltage across a resistor is equal to the current flowing through it multiplied by its resistance. Mathematically, Ohm's law is expressed as volts equals amps times ohms. This law is essential for analyzing and designing electrical circuits. Power in an electrical circuit is the rate at which electrical energy is transferred. It is measured in watts. The power dissipated by a resistor is given by the formula power equals volts times amps, which can also be expressed as power equals amps squared times ohms or power equals volts squared divided by ohms, using Ohm's law. Understanding power dissipation is crucial for selecting resistors with appropriate power ratings to prevent overheating and failure. A contactor is an electrically controlled switch used for switching an electrical power circuit, similar to a relay except with higher current ratings. Contactors are commonly used to control electric motors, lighting systems, heating, and other electrical loads. They are essential components in industrial and commercial electrical systems. Contactors typically have multiple contacts, allowing them to switch multiple circuits simultaneously. They are designed for frequent operation and can handle high inrush currents associated with motor starting and other inductive loads. The coil of a contactor is an electromagnet that, when energized, closes the contacts of the contactor. The coil is typically rated for a specific voltage, such as 120 volts or 240 volts, and draws a certain amount of current when energized. The coil is a crucial part of the contactor, as it is responsible for the mechanical action of switching the contact. When the coil is de-energized, the contacts return to their normal position, either open or closed, depending on the contactor's configuration. In electrical engineering, voltage refers to the electric potential difference between 2 points in an electric circuit. It is the driving force that pushes electric charge or current through a circuit. Voltage is measured in volts. Voltage sources, such as batteries and power supplies, provide the electrical potential difference needed to establish current flow in a circuit. Understanding voltage is fundamental to analyzing and designing electrical circuits. Current is the flow of electric charge through a conductor in an electric circuit. It is measured in amperes, often shortened to amps. Current is produced by the movement of electrons in a conductor, such as a wire. The amount of current flowing in a circuit depends on the voltage applied and the resistance of the circuit. Understanding current is essential for analyzing and designing electrical circuits and for ensuring proper operation of electrical devices. A silicon-controlled rectifier, or SCR, is a 4-layer semiconductor device used for controlling high-power electrical circuits. It is a type of thyristor, which is a solid-state semiconductor device with 4 layers of alternating N and P-type material. SCR are commonly used in power control applications such as dimming systems, motor speed control, and high-voltage DC transmission. SCR can switch large amounts of power and are known for their high efficiency and reliability. However, they have a characteristic known as halting current, which must be considered in circuit design. Holding current is the minimum current required to maintain an SCR in the on state. Once an SCR is triggered into conduction, it will continue to conduct as long as the current flowing through it remains above the holding current. If the current falls below the holding current, the SCR will turn off. The holding current is a critical parameter in SCR circuits, as it determines the minimum load current required to keep the SCR conducting. In dimming systems that utilize SCR, the SCR are used to control the amount of voltage applied to the lighting load. By varying the firing angle of the SCR, the average voltage applied to the lights can be adjusted, thereby controlling their brightness. However, the holding current characteristic of SCR can cause issues in dimming systems, particularly when dimming lights to very low levels. At low dimming levels, the current flowing through the SCR may fall below the holding current, causing the SCR to turn off and the lights to flicker or extinguish. To address this issue, a bleeder resistor is often added in parallel with the lighting load. The bleeder resistor provides a path for current to flow, even when the lighting load is drawing very little current. This ensures that the current through the SCR remains above the holding current, preventing them from turning off and causing flickering. The value of the bleeder resistor must be carefully chosen to provide sufficient current to keep the SCR on without wasting excessive power. Another method for addressing the holding current issue in SCR dimming systems is to use a triac instead of an SCR. A triac is a 3-terminal semiconductor device that can conduct current in both directions. Unlike an SCR, a triac does not have a holding current requirement. Once a triac is triggered into conduction, it will remain on until the current flowing through it falls to 0. This makes triacs well suited for dimming applications, as they do not require a bleeder resistor to maintain conduction at low dimming levels. However, triacs have some limitations compared to SCR. They typically have low current and voltage ratings than SCR, and they can be more susceptible to false triggering. The choice between using SCR or triacs in a dimming system depends on the specific application requirements. For high-power applications, SCR may be the better choice, while for low-power applications, triacs may be more suitable. In any case, it is important to understand the characteristics of these devices and to design the circuit accordingly to ensure proper operation. When working with electrical circuits, it is crucial to follow proper safety precautions to prevent electric shock and other hazards. Always disconnect power before working on any electrical equipment. Use insulated tools and wear appropriate personal protective equipment, such as safety glasses and gloves. If you are not comfortable working with electrical circuits, consult with a qualified electrician. Electric shock can be fatal, so it is important to take all necessary precautions to protect yourself and others. In addition to electrical safety, it is also important to consider fire safety when working with electrical circuits. Overloaded circuits and faulty wiring can cause fires. Make sure that all electrical circuits are properly wired and protected by circuit breakers or fuses. Never overload a circuit by plugging too many devices into a single outlet. If you smell burning or see smoke, immediately disconnect power and call the fire department. Electrical fires can spread quickly and are very dangerous, so it is important to take them seriously. When installing electrical equipment, it is important to follow all applicable codes and regulations. The National Electrical Code, also known as NEC, is a set of standards for the safe installation of electrical wiring and equipment in the United States. The NEC is updated every 3 years and is widely adopted by state and local jurisdictions. Following the NEC helps to ensure that electrical installations are safe and reliable. In addition to the NEC, there may be other local codes and regulations that apply to electrical installations. It is important to check with your local building department to determine which codes and regulations apply in your area. Failure to comply with applicable codes and regulations can result in fines, penalties, and even legal action. Electrical work should always be performed by a qualified electrician who is familiar with the NEC and other applicable codes and regulations. A qualified electrician has the training, experience, and knowledge necessary to perform electrical work safely and correctly. Hiring a qualified electrician can help to prevent electrical hazards and ensure that your electrical system is installed properly. When selecting an electrician, it is important to check their credentials and references. Make sure that they are licensed and insured. Ask for references from previous customers and check their online reviews. A reputable electrician will be happy to provide you with this information. It is also important to get a written estimate from the electrician before they begin work. The estimate should include a detailed description of the work to be performed, the materials to be used, and the total cost. Be sure to review the estimate carefully and ask any questions you may have before signing it. Once the electrical work is complete, the electrician should provide you with a certificate of compliance. This certificate indicates that the electrical work has been inspected and approved by a qualified inspector. Keep the certificate of compliance in a safe place, as it may be required for insurance purposes or when selling your home. Proper electrical maintenance is essential for ensuring the safety and reliability of your electrical system. Regularly inspect your electrical wiring, outlets, and appliances for signs of damage or wear. Replace any damaged or worn components immediately. Have your electrical system inspected by a qualified electrician every few years to identify and correct any potential problems. By following these tips, you can help to prevent electrical hazards and ensure that your electrical system operates safely and reliably.